Section 5.2, extreme point search, and we're going to define something called a basic solution and then ultimately a basic feasible solution. The first thing is, so we've determined that LPs, if they have an optimal solution, it has to occur at an extreme point. And so we're going to focus on an algorithm that's going to find extreme points, but we have to come up with a definition of an extreme point. Like, how are we going to identify these, given that we only have this AX equal B construction, right? So how are we going to do that? Well, every extreme point of an LP is determined by a set of constraints that are simultaneously active at that solution. So what does it mean, active or tight or non-binding? Remember, active was an inequality that was satisfied as an equality or an equality. Every equality is active. And so we have AX equal B, there's M constraints, but there's a set of those that we're interested in that are simultaneously active. Okay, well, all of our AX equal B are active. So there's really something else that's happening, and it's the simple constraints again. Don't forget about those. We have X greater than or equal to 0. Some of those will be satisfied as active equality equal to 0. And there's a set of those. So all the X B, those are always in our set of active constraints. And then we look at the simple constraints, and some of those will be turned on and turned out active as equal to 0. So we're going to take a look at this figure, which is on page 217 in a bit. Let's go through some of our terms here, though, some more definitions. Okay, so the simplex algorithm, though, it's going to actually move. It's going to start with an extreme point, so EP, and it's going to move from one extreme point to the next, always in an improving direction. And so actually, it's going to move to an adjacent extreme point. So that's something we need to define. Two extreme points are adjacent if they're active constraint sets differ in only one element of the set. Again, we'll see this in an example in a moment. And then an edge is a boundary line between two adjacent extreme points. So visually in R3, we can think about this on our polytope again. So here is an extreme point. Say that's the initial feasible extreme point that we found. We're going to move in a direction of improvement. So maybe I find a delta X. Turns out that that's got to be along an edge because I'm on the exterior of this. I started on the exterior, I'm on the exterior, I move an adjacent extreme point, and they differ in their active constraint sets by only one constraint, and I would get to this extreme point, which is an adjacent extreme point from this one. From here, I also find a direction of improvement. I'm going to move, perhaps it tells me move along this direction. I'm going to go in that direction as far as I possibly can until I'm no longer feasible, which actually puts me in another extreme point. Each time we're going to always check for optimality, but that's how the simplex moves. It actually is what's called a exterior. It moves along the exterior of the feasible region, and that's going to be as opposed to an interior point method, which we'll learn about in the next chapter, which would start in the inside and work its way to the outside. The simplex method starts on an outside in an extreme point, and it continues to move from one extreme point to the next until it's at the best one. So it's not necessarily, remember we talked about the brute force, I could just list all of them. How many are in this? 1, 2, 3, 4, 5, I think 8 of them. Just list them all and then pick the biggest one. The simplex algorithm for this might only have to go through 2 extreme points and then it'll know it's optimal. So it's much more efficient than total enumeration of extreme points, but it only considers extreme points as it moves. Every iterate of the simplex algorithm is an extreme point. Okay. Oh, one more definition, and then we'll take a look at this figure. So a basic solution, also called a BS, the EPs and BSs. A basic solution to an LP in standard form. So again, it has to be an LP and it has to be in standard form. It is obtained when you set enough of your variables to 0, and we'll quantify enough in a bit, so that the model's equality constraints can be uniquely solved for the remaining variables. And the ones that we set to 0 are called non-basic. All the other ones are called basic. So again, we're going to take an LP in standard form. We're going to select some subset of our variables and force them to be 0. Those will be called our non-basics. The other ones are basic. Okay, before we come back to this basic non-basic stuff, let's go to figure 5.3 on page 217. Okay, so page 217, there's this figure of a polyhedron that is finite, makes it a polytope in R3. There's faces that are defined here that we can see. This face right here, he's labeling A. It's defined by these constraints. 1, 2, 3, 4. Then here's a face B. And let's just identify a few of them and talk about what are active constraints. So let's go to the point x0 down here. So this is actually showing the path of an extreme point search. Something that the simplex would do. It starts an extreme point, moves from one adjacent extreme point to the next through these iterates: x0, x1, x2, x3, x4, x5, x6. Okay, let's focus on x0. Which constraints are active here? So it's at this point right here, any of the, this point is defined by, you can think of as the intersection of faces. And so here's a face J, here's a face I, and there's actually a third one. It's not labeled, but it's the floor, the bottom floor here of this polytope, right? It's sitting on something. And that is when x3, the Z component, is 0, right? You're down in the x1, x2 plane. So x0 is actually defined by the constraint given by I. So again, this is a face defined by a plane. So I is a plane, J is a plane, and x greater than or equal 0 is a plane when x3 equals 0. So we have 3 planes, they intersect and make this point x0. Now x1 is defined by I, J, and G. x2 is actually defined by the intersection of 4 planes, G, J, D, and C. x3 is defined by 5, I, G, C, B, and H. x4 is A, B, C. x5 is A, C, and the back wall here, which is when x2 equals 0. Okay, so let's take one that had, let's take x2. This is one that had 4 constraints that could be used to define it, but if you set any 3 of those, you just need 3 of them, right? To define a point in 3-dimensional space, I need the intersection of 3 of these, so any 3 of them would work. So I really have more than I need, and same thing at x3, I have more than I need. Of these 5, any 3 of them can be used to define set. So constraints that are active depends on which point you're at and how many there are. Okay, let's look at x1. Say we're at x0 and we want to go to x1. Let's again talk about how they're adjacent. Clearly we can see that from a picture, but how are we going to do this in n-dimensional space? Well, the definition of adjacency was that the set of active constraints differ by only one element. So the set of active constraints at x0, we said was I, J, and x3 equals 0. And then at x1, it's I, J, and G. So again, they differ in that x3 equals 0 or the G, therefore they're active. And you can go ahead and walk your way through this and keep listing the active constraint sets at each and see that they do differ in just one element. So for instance, like let's go from x2 to x4. Clearly not adjacent. There's no way to get there. You have to go through x3 first. You can't just travel through the middle of a face. That's not how the simplex works. It's impossible for us to do that. So they're not active, and let's just check that that's true from the definition. x2, its active constraint set is G, J, D, and C, and x4's is A, B, C. So they don't differ by just one element. They're quite different. Okay, what else do we have? Oh, an edge. So from 3 to 4, yeah, from this point 3 to 4, that's an edge, clearly from the picture, but how can we think about this in higher dimensional space? That edge is defined. It's the boundary line between two adjacent extreme points. And it's when both B and C are active, right? So the intersection of two planes can make a line in R3, which is this edge. Okay, let's then maybe talk about this last statement. A basic solution is obtained by setting enough variables to 0 so that the remaining constraints can be uniquely solved. And those are non-basic. So how do you know how many and which variables you should set to 0? So how many and which should be your non-basics? How are you going to know that? And does it even matter? Yes, it certainly matters. And what's left over, remember, those are called basics, all the other ones. Well, how to get the name basic? If you have a hint, think about your linear algebra, if they form a basis. So if your basic variables, the ones that are left over that weren't set to 0, if those form a basis, they're columns, take those columns out of A, and if they form a basis, then you have enough and it uniquely solves it. Okay, so let's work through a couple examples and we'll get used to that language and that vocabulary. Okay, I want to look at this example, and I think it'll help us understand the basic and non-basic terms, how they got their names, and we'll get to review some linear algebra. Okay, this is number 5 at the end of chapter 5, so 5-5. They give us this constraint set. We don't need to know the objective function because they're just asking which of these variables should we have, basic and non-basic. So from this constraint set, we put it in standard form. We're good here. The only thing we need to do is handle these main constraints. We add some slacks in, and now we're in standard form. It has to be in standard form before you can start this analysis of which ones should be basic, which ones should be non-basic. In this problem, he gives you a few questions. He says, does the set of variables, if you chose y1 and y2, do they form a basic set? And then he says later on, what about y2 and y3? What about y1? What about y2 and y4? And he goes on trying different ones to see, do they form a basic set? And then we'll see the commonality by doing this, what happens, get a better sense for what a basic set is. Okay, so if these are your basic variables, that means everybody else is non-basic. Well, who's everybody else? In this case, that's y3 and y4. What does it mean to be non-basic? It means you're forcing them to be 0, right? So this is just language and definitions. So y3 and y4 are 0. So that means this constraint set, these guys go to 0. And what you're left with is y1 plus 2y2 equals 6, y2 equals 2. You can pull off the coefficients associated with that and put that in a matrix. This is a matrix that is really a subset of the entire A, right? If we were entering this into MATLAB, your A matrix would be 1, 2, 1, 0, 0, 1, 0, 1. And so we've pulled off columns of A that correspond to the basic variables. This corresponds to y1, this corresponds to y2, but there was 2 more columns, right? We pulled off that submatrix and we're asking ourselves, does that make a basis? What does it mean? What does it mean to be a basis? What does it mean to be a basis in R2 in this case? Because we're in m-dimensional space because there were m constraints, 2 main constraints, and we're in m-dimensional space. What does it mean to be a basis in R2? You need to span the set, all of R2. You need to have rank 2. You need to be a set of linearly independent columns. All those mean the same thing, which clearly it does span the set. This is a basis check. So question, was y1 and y2 a basic set? Yes, because when you set the non-basics to 0, what you're left with is a basis. And the reason it's valuable for us, because then we can solve this and get values for y1 and y2, right? So y2 must be 2, and therefore y1 must also be 2. So we'd have the solution associated with this one, or write it as a row vector, is y1, y2, y3, y4, which is given by 2, 2, 0, 0. Right? So we're able to get an actual solution, which then lives on our polytope. All right, what about y2, y3? Is that a basic set? To be a basic set, so here's a question. That means the non-basics would be y1 and y4. We're going to set those to 0. And then we do the same thing. So if y1 and y4 are 0, these columns drop out, and we're left with, is this matrix full rank? Yes. In MATLAB, you just say, you can put in, if it's a bigger matrix and you don't want to do it by hand, you just say rank of A, and it'll split back 2. But that's clear to see from this one that we don't have to do anything. It's a reordering of the rows and columns, and it's in row echelon form, clearly rank 2. So this one also is a basis. And what happens then for our basic solution? Let's see, we'd have y transpose would be y1, y2, y3, y4. We forced y0 and y4 to be 0. They were non-basic. We saw what happened to the y2 and y3. Let's see, what we're left with is y2 is 2, y3 is 6. Is that right? Oh no, sorry. Y3 is 2 again. Right, because 2 times 2. So I'm just solving this little subsystem here. Okay, what about y1? Well, that would mean everybody that's not y1, which is y2, y3, y4, we're going to set to 0. Those are your non-basics. That means this drops out, this column drops out, this column drops out, and we have this system, y1 equals 6, and 0 equals 2. See the problem here? Doesn't make sense. This one has no solution, so this is not a basis. You can't just take one unknown and solve for 2. Okay, y2 and y4. Let's check those out. The non-basics would be 1 and 3. Set those to 0. A is the columns corresponding to y2 and y4. And those would be 2, 1, 0, 1. Yeah, that'll do it. And I think he's got one more for us. Oh, a couple more. I'll erase the board, make space, because we've got a few more examples. Okay, let's try these 2 more sets that he gives us. Is y2, y3, y4 basic set? That means what's left over. The non-basic is there's only one variable left over. y1 equals 0. And so then the A matrix that's left that we need to solve for has y2, y3, y4 columns. And that would be 2, 1, 1, 0, 0, 1, which is a 2 by 3. Well, this is a underdetermined system, right? We've got 2 equations, 3 unknowns. And so we can't find a unique solution for this. We have and actually there's some dependency between the columns. So not enough, an underdetermined system, right? So we can't get a unique solution. So not a basis. Okay, next one. So too many there. So you have to have just the right amount. And so this looks like the right amount because in the previous, if we had a hunch from the previous one, it seems like 1 was not enough, 3 is too many, 2, and that seemed to work. Well, let's see if these 2 work. So the non-basics here would be y2 and y4 equals 0. So what we're left with, the A matrix, which is a submatrix pulled out, corresponding to columns 1 and 3. Which is 1, 0, 3, 1, 0. All right, but what's the problem here? This is not full rank. Actually, it's linearly dependent columns and rows. I'm going to look at it. And rank equals 1, so not a basis. So it's not enough to just pick out the right number. That's why he said you have to have the right number, but they also have to uniquely solve the system. So it's important. It's not so easy as just trial and error picking these to form a basis. Another way to check. So we talked about you could do REF on this, you could do rank, you could do linear, just visual inspection, but remember, you could also check the determinant, and he's got a nice primer number 4. If you don't remember your linear algebra, check out primer number 4. And it talks about if the determinant is non-zero. If this thing turns out to be non-zero, you know your system what A is non-singular. And that means it has a solution, linearly independent columns with a unique solution. And in MATLAB, you just say DET of A, and it'll give you that. So another easy way to check on some of the larger problems. Okay, let's erase the board. Okay, last couple of comments here are really big ones from the end of 5.2. So the question is, does this process for creating a basic solution, which was pick some non-basic variables, set them to 0, solve for the remaining basic variables, does that guarantee that that solution, that basic solution, is a basic feasible solution? Because again, we have to be feasible. We need to be moving around the edges of this. We can't be outside the feasible region. Well, no, it doesn't. So solving the inequalities for the basic variables might produce a unique solution. That's what we wanted. But you could have some negative values, and therefore it's not feasible, because if it's in standard form, we need every one of our variables to be non-negative. So go to the table on page 225, table 5.1, but we can also look at it just from our previous example. So in that previous example, there was he asked you to check out this basic set, Y2 and Y4. He said, does that form a basis? Yes, it did. And the basic solution that we found, we didn't go through all of this. We just said, check. It was a basis. It had rank 2 when we pulled out those 2 columns. But the problem was, if we actually went one step further and solved that little system that was left, we set Y1 and Y3 to 0, no problem. But when we solve the remaining system, we would get 3 and -1. The -1's the problem here, right? That's not a feasible solution because we need non-negativity in all of our variables. So it's possible in doing this that your basic solution is not a basic feasible solution. We need basic feasible solutions. So a basic feasible solution is a basic solution that satisfies the non-negativity. So this was a BFS. It's not a it's a BS. It's not a BFS. But here's the coolest theorem. A basic feasible solution for an LP that's in standard form. Those basic feasible solutions, there's a 1-to-1 correspondence with the extreme points of the feasible region. Remember, we're super interested in those extreme points. Hey, they're basic feasible solutions. And this is what got Danzig and his algorithm going. So he had a way of using linear algebra to get basis, a basic solution, and if you could just check if it's a basic feasible solution. If it's a basic feasible solution, you're an extreme point. Okay, now how am I going to get to the next extreme point, an adjacent one? And that's really what simplex is going to do, and we're going to get there in the next few sections. Okay, so 5.2, there's just one problem to look at, number 4. This is on page 246.